So n equals 2 case, you got 2 half wavelengths. N equals 3 case, you got 3 half wavelengths, because we got to start and end on a node. And in general, for the nth case, we can extend this. For any nth harmonic, what can we say about L compared with lambda? What would be the relationship between the length of the string and the wavelength of the wave? Can we generalize this idea? Yeah. In general, if you have the nth harmonic, you need to have n copies of a half wave. So the length of the string has to be n half wavelengths, n times lambda over 2. And it's got to be a whole number of waves or a whole number of half waves, because if you have a non-whole number of half waves, you don't start and end at a node. And then if you solve that for lambda, what do you get? It's not so much, I mean, the over 2 is really because we're counting half wavelengths. We're not counting a whole wavelength here, because a whole wavelength is too long. We just want to know if you go from node to the very next node, because you've got to go from a node to another node. That's a half a wavelength. If you go from this node to the next node, that's half a wavelength. To the next node is another half wavelength. From node to node, half a wavelength, then another half wavelength, then another half wavelength. From node to node is always half a wavelength. So if you start at a node and end at a node, you have to have a whole number of those half wavelengths. Note that this is also true if you have antinodes on both sides. If you've got like a, and this doesn't really show up with strings, but let's say you've got something like maybe the metal plate from a xylophone. A xylophone is a fairly loose metal plate that's very, very loosely suspended on a couple of pegs, but the ends are largely free to vibrate. So what kind of points would we expect at the ends if they're free to vibrate? Yeah, lambda is going to be, if we solve for this algebraically, 2 times L over n. If we isolate lambda, multiplying by 2 divided by n, we get the wavelength has to be 2 times the length of the string divided by n. If it's free on both ends, though, what kinds of points have to be occurring at the endpoints if they're free to vibrate? Not just anything. If they're free to vibrate, what do we call a point that is most free to vibrate? Like if this is just a metal bar where the ends are not attached to anything. Yeah, if the ends are not attached to anything, if they're free to vibrate, we would call that an antinode. So you'd have antinodes at the ends. And then in between, the simplest example would be to have a single node. So the n equals 1 case would look something like this. Antinodes on the ends, a node in the middle. However, how much of a or what fraction of a wavelength is it? If we're going from an antinode to the next antinode, what fraction of a wavelength is that? It's more than a fourth of a wavelength, because if you take a look at a complete wavelength, if you go from, let's say, a crest to equilibrium, that's a fourth. But yeah, crest to equilibrium to trough, that's an entire half of a wavelength. And you can even see this if you continue this. Continue this to the next crest. From crest to crest would be 1 wavelength. But to go from antinode to the next antinode is equivalent to going from crest to trough. That's half a wavelength. So from node to node was half a wavelength. From antinode to the next antinode is also half a wavelength. So if you've got even a much more complicated free standing wave, let's say you've got metal bar that's free to vibrate on both ends. So you've got antinodes on the ends. And let's say you've got a pattern of several antinodes and nodes. Maybe something like this. So you might have a fairly complicated looking pattern, with each antinode again representing a point that is vibrating wildly, large amplitude, and each node representing a point that's hardly vibrating at all. But again, if we take a look at this in terms of half wavelengths, half a wavelength being from a node to a node or an antinode to an antinode, there's a half wavelength, there's a half wavelength, there's a half wavelength, and there's a half wavelength. So that's still a whole number of half wavelengths. In fact, since this is 4 half wavelengths, we would say this is the n equals 4. This is the 4th harmonic. As opposed to the fundamental harmonic, the fundamental vibration. N equals 1, the first harmonic. So once again, n still represents the number of half waves, which means we can still say that the length of the bar is n half wavelengths. And if you solve that for lambda, you still get 2 times L over n. So this formula, the idea that wavelength is 2 times the length divided by some whole number, the harmonic number, this applies equally well to a string that's fixed on both ends or a metal bar that's free on both ends. As long as both ends are the same type, if they're both nodes or if they're both antinodes, you get the same formula. The wavelength has to be 2 times the length of the bar or string or whatever, divided by n, the harmonic number. Any questions on that so far? However, if you're listening to this, like let's say you pluck a string on a guitar and you're listening to it, the wave isn't only traveling in the string, because you don't have to like hold the string up to your ear to hear it. The wave travels from the string through what else to get to your ear? Yeah, the sound is largely traveling through air. The wave is created in the string's vibrations, but the string vibrating causes the air to vibrate also. The string moves this way, creates high pressure zone of air. The string moves this way and creates suction, creates a low pressure zone of air. As the string vibrates, it causes the air locally to oscillate between high pressure and low pressure, and that spreads out as a sound wave. Then the sound wave hits your ear and causes your eardrum to vibrate as well. And as sound transitions from one medium to another, the wavelength changes because the speed changes. But what stays the same as it goes from medium to medium? What else is related to wavelength but doesn't change as you transition from one medium to another? Yeah, the frequency. I would say the velocity does change because velocity depends on medium, but the frequency is going to stay the same. The frequency is determined by the vibrations of the string, but then the frequency stays the same as the wave transitions from string to air to your eardrum. Those are all vibrating at the same frequency. So frequency is usually what we talk about when we're describing the sound you actually hear. We have a formula for the wavelengths that can be created by this string or by this metal bar from a xylophone or something. But how would you convert that to a frequency? What's the relationship between wavelength and frequency? Yeah, we can use the speed equation that speed is wavelength times frequency. And if you solve that for frequency, you should just get speed over wavelength. And we have a formula for wavelength. Wavelength is this fraction, 2L over n. And dividing by 2L over n is the same as just multiplying by its reciprocal. So speed times n over 2L. So this gives us a formula for frequency. The frequencies of sound that can be produced by this string or by this metal bar are speed times n, where n can be any whole number, divided by 2 times the length. Or sometimes a better way to put that, frequency is speed over 2L times n. Since n can be any whole number, but speed is going to be a constant and length is going to be a constant. And that speed, by the way, that should be speed in what material? Where is the wave being created here? Yeah, the wave is being created in the string, or in the case of the xylophone, in the metal bar. So the V here, since we're talking about being created, the location where the wave is created, this V should be the speed of the wave in the string, or the speed of the wave in the metal bar. So that'll be speed of the wave in the medium where it's created, divided by 2 times the length of the region where it was created, times any whole number, where n is specifically the harmonic number. So for the fundamental frequency, the fundamental vibration, you would use 1 for n. And then for the next harmonic, the second harmonic, you would use n equals 2, then n equals 3, n equals 4. So there are many frequencies, in fact, infinitely many frequencies that could be created by that length of string. But typically you would only hear the first few frequencies. If we take a look at those frequencies though, some space here. The text. If we take a look at some of those frequencies, let's see if we can establish a pattern. So if we take a look at the various harmonics, for the n equals 1 case, if we just fill in 1 for n, we get V over 2L. We would probably call that F1. So V over 2L is the fundamental frequency. That's the lowest note this string can produce. If we plug in 2, though, we just get twice as much as the fundamental frequency, 2 times V over 2L, which could be reduced to V over L. But I think the important thing here is that it is twice as much as the fundamental frequency. Or F3, it's going to be 3 times V over 2L. So that's 3 times as much as the fundamental frequency. In the fourth harmonic, we'd have 4 times V over 2L, which is 4 times the fundamental frequency. So this string, like if you just take a string and pluck it and let it vibrate, you're not really telling it to vibrate at a certain rate. You're just creating this chaotic jumble of many frequencies at once. But the only frequencies that actually perpetuate, rather than just dying off immediately, are the ones that fit this pattern. V over 2L, or twice that much, or 3 times that much, or 4 times that much. Those are the only frequencies that match wavelengths that fit in the string as standing waves. Any questions on that so far? And if you take a look at the transitions here, let's say you go from F1 to F2. How much changes that if you change from F1 to F2? What's the multiplier there? Yeah, changing from the fundamental frequency to the second harmonic is a ×2 multiplier to the frequency. And anyone know what happens to the sound if you double the frequency? What would actually sound different about that? It is a higher pitch. If you increase the frequency, you get a higher pitch note. But doubling it specifically, we can go a lot more specific than that. If you double the frequency exactly, that actually corresponds to going up exactly 1 octave. So that's going to sound like from a low G to from a low G to the next G up. So that's doubling the frequency. And that sounds that can be produced by the same string. If I just pluck this string, you're mostly hearing the low G, the fundamental frequency. This is a mandolin. It's got 8 strings, but they're in pairs. So 2 of them in the same, 2 of the same note, then 2 more of the same note, 2 more, 2 more. So 4 different notes. But this string is producing a note, a low G, as the fundamental frequency. But it's not just a flat tone of it's not just that note. It sounds richer because it's producing also twice that frequency and 3 times that frequency and 4 times that frequency. It's got a blend of several different frequencies that sound good together because they're all from the same string. They're all harmonics of that one fundamental frequency. And that's why that note sounds good with other notes. These 2 notes, an octave apart, sound good because one of them is a multiple, a nice neat whole number multiple of the other. And likewise, F2 to F3. If you go from F2 to F3, what's the multiplier? What do you have to multiply this by to turn it into this? It's 3 times the original, but if you start at 2 times F1, what do you have to multiply by to get to 3 times F1? What's the multiplier that turns 2 into 3? Yeah, times 3 halves, or 1.5, yeah. So that means from the second harmonic to the third harmonic is a 1.5 multiplier, 3 halves. And that turned out to correspond to major 5th, I think. There we go. So a major 5th, or this interval, that's a 1.5 multiplier. That's another pair of notes that sound good together because they're nice, neat, not whole number multiples of each other, but a convenient fraction, 3 halves or 1.5. Or then if you go from 3 to 4, what's the multiplier there? Right, times 4/3, or 1.3 repeating. So that's another nice, neat, convenient fraction of simple whole numbers. And that's another pair of notes that sound good together. If I remember correctly, that's a major 4th. If we combine those together though, let's say you jump from 2 directly to 4. How much of a jump is that? What would you have to do to 2 times F1 to turn it into 4 times F1? Right, that's another times 2 jump, which means how far off are those 2 notes? That's exactly times 2, so that's going to be that should be exactly another octave. So we go from, let's say, low G to the next G up, and then to the next G above that. So from G to the next G to the next G. That's the first, second, and fourth harmonics. And then the third harmonic is another note between the G and the G that sounds nice together, forming a chord. So you can, this is ultimately the foundation of all of music theory, that certain notes sound good together because they can be produced by the same string. They're just different harmonics on that same string. With an O, yeah, O-C-T-A-V-E. So that's, and it's called an octave because we split it up into 8 pieces from one to the next. So 8 notes in a scale. That 8 notes is just sort of a convention. Different cultures sometimes use different scales. But the idea of a note and exactly twice that frequency sounding good together is pretty universal. Any questions on that so far? And any other questions on standing waves in general? There's also standing waves in pipes, by the way. If you have, this works well for stringed instruments. But if you've got a wind instrument, like a flute or a clarinet or something, instead of a string, let's say you have a pipe full of air. So instead of making the string vibrate, you're making the air inside the pipe vibrate. So if you've got a pipe that's open on both ends, would you consider the endpoints to be nodes or antinodes? That is, at the endpoints, would you expect a lot of vibration or just no vibration at all? Antinodes, yeah. If we're specifically talking about the air's ability to move around, like if you consider an air molecule vibrating, if the end is open, and actually it kind of depends on how we treat the sound wave. If you treat the sound wave as air molecules vibrating, an open end means the air molecules are free to move around quite a lot. So we would treat these as open ends as antinodes if we're talking about displacement. So sound as a displacement wave. That is, if we're talking about, there's kind of 2 different ways to think about sound in air. You could think of it as displacement wave. That is, the individual air molecules vibrating. In that case, an open end would be an antinode. Because an open end means there's nothing in the way. The air molecule is free to vibrate loudly. And then a closed end would be a node, like if you have a wall on one end of the pipe. That wall prevents the air molecules from moving very much, so that would be a node, a displacement node, in the sense that the molecules can't move. So if you think of the sound as a displacement of the air molecules, like the individual air molecules physically moving around, then an open end would be an antinode because the molecules are free to move, and closed end would be a node because the molecules are blocked by the wall. But if you think of the sound as a pressure wave, that is, instead of caring about how the molecules are moving, if you think of sound as oscillations in pressure, like this location in the air is oscillating between high pressure, low pressure, high pressure, low pressure, as the sound passes by. If one end is open to the air around it, what pressure does that end have to be at if it's open? Think back to 7b when we were looking at fluid flow and pressure. If you've got something that's open, exactly, it has to be at atmospheric pressure. And if it has to be at atmospheric pressure, that means the pressure cannot change. If the pressure can't change, would you consider that to be a node or an antinode? If the pressure has to be 1 atmosphere, so there's no oscillation in pressure, exactly, that would count as a node. So if we're talking about sound as pressure, the open end is a node because the pressure must be at 1 atmosphere. Whereas a closed end, if you've got a wall on one end of the pipe, then that could be at any pressure at all because the air can push on the wall and pull on the wall, and the wall's not going to move. So the wall since this is closed off from the atmosphere, that wall allows this air to be at any pressure. So that would count as an antinode. The closed end is an antinode as far as pressure is concerned, because the wall allows any pressure to happen. So the pressure is able to vibrate as the air pushes and pulls on the wall without moving it. So displacement wave and pressure wave are going to lead to opposite sorts of diagrams. Like if we treat the open end as a antinode and the closed end as a node, we would get this sort of shape. And how much of a wavelength is that? What fraction of a wavelength is it from crest to equilibrium? Yeah, that's a fourth of a wavelength. So in this case, we'd say and we would call this the fundamental vibration as well. In other words, n equals 1. We'd say the length of the pipe is a fourth of a wavelength. On the other hand, if we treat this as a pressure wave, we would have to treat the open end as a node and the closed end as an antinode. So it would look like a rather different diagram, exactly flipped. But in that case, how much of a wavelength is that? If we're going from a node to an antinode, what fraction of a wavelength is that? Half would be from a node to the next node. If we're going from just a node to the next antinode, how much of a wavelength is that? Yeah, that's still a quarter. So we still get length of the pipe is a fourth of a wavelength. So even though the diagrams look different, the mathematical result is the same, that the fundamental vibration is length of the pipe equals a fourth of a wavelength. So in terms of the equation, it doesn't really matter if you treat it as a displacement wave or a pressure wave. It doesn't matter which end counts as an antinode and which end counts as a node. The important thing is if the two endpoints are different kinds of endpoints, an open end at one end and a closed end at the other end, then you've got to have a fourth of a wavelength to get from one to the other, regardless of whether you treat it as a pressure wave or a displacement wave. However, let's say we have a more complicated harmonic. Instead of just going from an antinode directly to a node, let's say we put another node in between and another antinode in between, because we've got to alternate, evenly spaced. In that case, our standing wave is going to look kind of like this. And since we're changing from an antinode to a node, it would still be a good idea to count quarter wavelengths. How many quarter wavelengths is this? If we're going from antinode to the next node, and then from that node to the next antinode, then from that antinode to the next node, yeah, that's 3 quarter wavelengths, 1, 2, 3. So we'd say in this case, for the next harmonic, we'd have 3 quarter wavelengths. So we'd say the length of the pipe is 3 times a quarter wavelength. So we've got the fundamental harmonic would be 1 quarter wavelength. The next one would be 3 quarter wavelengths. And then we could make this one more step complicated by having, what would be the next one? Could we do 4 quarter wavelengths? Problem is, if we do 4 quarter wavelengths, yeah, it's going to have to go to 5, because if we do 4 quarter wavelengths, 1, 2, 3, 4, that would actually be a node on both sides. And that doesn't work if the pipe has different types of endpoints. These red vertical lines, I'm just marking at every node and antinode. Because for the fixed, or free, we were counting from node to the next node, or from antinode to the next antinode. But in this case, since we start on one type of point and end on the opposite type of point, antinode to node, it's a good idea to count from antinode to node, node to antinode, antinode to node. This is why quarter wavelengths become important here. And since we want to start and end at opposite types of points, how many quarter wavelengths do we have to have? Like, why was it that 3 quarter wavelengths worked, but 4 quarter wavelengths didn't work? Yeah, it's got to be an odd number. 3 quarter wavelengths will form a standing wave in this mixed pipe, open end and closed end. 5 quarter wavelengths would work. 7 quarter wavelengths would work. But it's got to be an odd number of quarter wavelengths in order to get from an open end to a closed end, or vice versa. So generally we can say it's got to be an odd number of quarter wavelengths. If you solve that for lambda, what do you get? Yeah, L divided by an odd number times 4, or 4L over an odd number. And we could write that odd number usually as 2n minus 1, but I usually just think of it as 4 times L over an odd number. And by the way, for the fixed n or free n, you could also treat that as 4L over an even number. That'll reduce to 2L over n anyway. And then to change that into a frequency, we do the same thing, speed divided by that wavelength. So frequency would be speed divided by this wavelength, or times its reciprocal. So speed times an odd number divided by 4L. Or to put it another way, speed over 4L times an odd number. So once again, we have a fundamental frequency, in this case, V over 4L instead of V over 2L. And instead of times any whole number, we just have times odd numbers. So we've got a fundamental frequency and 3 times that much, and 5 times that much, and 7 times that much. So we get a different pattern of harmonics. We still get multiples of a fundamental frequency, but in this case, only odd multiples. We're skipping the even multiples. And among other things, that means we don't get octaves. If you've got a pipe that's open on one end and closed on the other, you don't get octaves. You get the fundamental frequency 3 times that much, 5 times that much, but you skip all of the even harmonics, or skip all of the even multiples. So it's going to be a very different sort of characteristic sound. And this is a big part of why different instruments sound different. If you've got like a clarinet and a trumpet and a fiddle and a guitar all playing the same note, they're still going to sound different because they're producing sound in different ways. But in general, these are the only formulas we're going to need for these. If the endpoints are the same, you can always use speed over 2L times n. If the endpoints are different, you can always use an odd number times V over 4L. Any questions on all that sound harmonic stuff? All right, try applying that to any practice problems you've got for that, and we can take a look at more examples and or how this applies to quantum mechanics next time. See you then. You're welcome.